So on this page, on example 5, we have an explanation here of what's called a composite function. It's basically what we just did in example 4. But they're introducing this new symbol to you, this little O. You see it right there between the G and the F, right? Let me write it a little bit larger up here. Sometimes we call it fog X, all right? You might see it written like that, F-O-G with just a little X in parentheses. You might see it written like that with both of those in parentheses. We're pretty lenient about this. Sometimes you might see a teacher just write it like that, F-O-G, and not even leave the X there, all right? That's the lazy way to do it. So that's what I usually do, all right? So all it means is you're putting G of X inside F of X, all right? Instead of the analogy with the shampoo and the conditioner, I think it might make more sense if we think of these composites or these compositions of functions as one machine built inside another machine, all right? For example, if you've ever done laundry, you know that you have to put your stuff in the washer, and then when it's done, you got to take it out and put it in the dryer, right? They're two separate machines. Wouldn't it be nice if there was just a machine that washed your clothes, and then when it was done, it dried them? That would be awesome, right? That would be a machine inside another machine. So that idea of like an all-in-one machine is what we have here. We have a function inside another function right here. F-O-G. Let's go down to example A. F-O-G is saying, take the G of X machine and embed it, put it inside the other machine. So you have this outside F of X taking the square root of whatever you put in plus 7, right? So that would be like the overarching machine. I'm not the first one to use the analogy of a machine. It's a very common analogy that math teachers use for functions. The function rule. What is this thing doing to the input, right? Well, F is adding 7 and square rooting it. G is a different machine. And we're placing it inside the F of X machine. 2x minus 5 is now built in to the F of X machine. So G of X is inside F of X. All right? What we typically ask you to do is simplify if you can, and you can. Because 2x minus 5 plus 7 is 2x plus 2. They didn't ask us to do this next step, but we're going to do it anyway. Would the machine be different or look different if you did it the other way? Would a washing machine, dryer machine combination be different if it dried your clothes first and then washed them? Yes, right? There'd be a different result. Would this be different if the outer machine was taking 2 times x minus 5, and then on the inside, built in, you were taking the square root of x plus 7? Yes, I think our results would vary between the two based on the order of operations. This is 2 root x plus 7 minus 5. So G of F is not the same as F of G. Okay? Let's actually write all that over here. Can F plus G be reversed? Everybody say yes.
Yes.
Good. Can F times G be reversed? Yes. Can subtraction be reversed?
No.
No. But like maybe, but only in rare cases, right? So F minus G is not the same as G minus F. And then division. We talked about some of this yesterday, right, G? F over G is not the same as G over F. Well, today we're learning, based on that example right there, you would get totally different results here. Fog is not the same as Goff. All right? F of g of x is not the same as g of f of x. If you're watching this on video, go ahead and do part B. I'll pause, and then you can check your work. I started up the video again just to make sure that if you're watching, we just talked about how this is important, that you do the 4 minus x squared the long way by FOILing it out. 16 minus 8x plus x squared. Now we're just going to clean this thing up by saying x squared doesn't have any like terms. Negative 8x can combine with negative 1x to make negative 9x. And 16 plus 4 plus 2 is plus 22. So this would be f of g of x.